Hello everyone, my name is Zhaoyang Ma and I'm a graduate PhD student from Monash University. I had a great time in Melbourne and I would like to express my sincere gratitude to my master provider, Professor Ranjith. Professor Ranjith is the director of 3G Deep Group and also he is a fellow of Australian Academy of Technology and Engineering. In addition, Professor Ranjith is the best in the world in mining and mineral resource engineering. He is also the field leader in environmental and geological engineering. I've graduated in December 2021, and the title for my thesis is Probing the Micromechanics and Thermal Expansion Coefficients of Granite rock-informed minerals. In the following slides, I will briefly introduce part of my PhD research. The main aim of my research is to probe the micromechanics properties of granite, and this study has been divided into three parts. In the experimental study, the structural information as well as the material properties such as the micromechanical parameters, thermal expansion coefficients have been extracted, and the method we have been utilized is that 2D and 3D characterization method as well as numeric nano-intention, nano-scale, as well as the in-field XRD. After that, numerical simulation study has been carried out in order to validate and to complement with our experimental study. Last but not least, various methods have been utilized to upscale our micromechanics properties that we have gained from nano-intention as well as nano-scale. Normally, Young's modulus and harness can be extracted directly from nano-intention test. For our study, apart from Young's modulus and harness, various parameters such as the fracture toughness, time-dependent creep, stress strain curve, elastic and plastic work can be extracted from a nano-intention result. Because nano-intention is a high-resolution technique, therefore the sample size is quite small. Therefore, we have to cut our sample, grind our sample, and then we have to polish our sample. After the polishment, we need to measure the surface roughness of our granite sample, and we have to make sure that our sample is suitable for both nano-intention, nano-scale, as well as the ABS-C test. Before we carry out nano-intention, we need to obtain the structure and also the phase composition of granite sample. Therefore, the powder XRD have been carried out. We found that the granite from South Australia Kalabari mainly composed of coarse microcline and white with small amount of mica and chlorides. Apart from the room temperature XRD, both high temperature XRD as well as the low temperature XRD have been carried out. And according to the in-field XRD, the unit cell as well as the temperature-dependent thermal expansion coefficient of granite rock-informed minerals have been extracted. Apart from the XRD, both thin section test as well as the SEM-EDS test are also carried out, and we compared the result from these three tests. It is found that the result is not consistent with each other because the observation size. Therefore, we have performed the TIMA test in order to get the large area mineral composition. From these slides, we can see that we can obtain the mineral composition as well as the pore size from our granite sample directly. In addition, the EBS-C test have been performed in order to obtain the grain boundary, grain orientation, and these EBS-C maps have been utilized as the input data for the homogenization analysis. It comes to my study about nano-intention. There is an optical microscope in the nano-intenter, and we use this optical microscope to locate the area that we are interested. After the relocation, we can carry out the grid nano-intention test, and from this intention test, both the load versus displacement curve can be extracted, and according to this curve, both Young's modulus and harness maps can be extracted directly. Because our granite sample is a heterogeneous material, which means it's composed of multi-phases. Therefore, deconvolution method have been adopted to extract the reduced Young smallness and hardness of each single phase. Apart from that, we also carry out nano-indentation to obtain the mechanical parameters near the ground boundary and in the ground boundaries. And we found that both Young modulus and hardness of the ground boundary is about 1/5 of the average value of the two phases. Then we carry out nano-indentation to obtain the frag toughness and also the time-dependent creep of our sample. And we use two different models, that is a 3-element volume model as well as the budget model to fit our nano-indentation creep results. Although nano-indentation is powerful technique, it still has disadvantage. That is, it can only obtain the mechanical parameters of each single point. It cannot detect the mechanical parameters continuously. Therefore, nano-scale test has been carried out. We use nano-indentation test to obtain the frag toughness of our granite sample, and it is found that two results agree well with each other. We changed the end load, and we also found we also used nano-scale to obtain the frag toughness, coefficient of friction, as well as the AE accounts. Then we performed the SEM to obtain the nano-scale. It is found that the fluctuation of calculated frag toughness is due to the brittle damage and the high penetration load, and the unstable value of Ft is due to the generation of debris particles and chips on the indenter along the groove. Here comes my second study, that is the numerical simulation. We perform the molecular dynamic simulation, and we study the impact of the indenter shape and also the impact of the grain size, temperature, as well as the indentation size. We compare the result with the nano-indentation experimental study, and it is found that the result agrees well with each other. We also use molecular dynamic simulation to uncover the deformation mechanism underneath the indenter, and we found that both for conical indenter, both the reduced Young's modulus and the hardness decrease with the contact depth first, then they will increase with the contact depth. Here we show that we use molecular dynamic simulation to we use two parameters, that is the volumetric strength as well as the shear strength, to uncover the deformation mechanism underneath the indenter. Apart from the molecular dynamic simulation, we also carried out the finite element simulation because we want to obtain the stress strain curve directly from nano-indentation. So how can we obtain the stress strain curve from nano-indentation? That is, we have carried out the inverse analysis. We used the modified DPCAM model, and we found that the both numerical results agree well with the experimental result. And also, during the numerical simulation, there is the issue that is called the non-uniqueness issue. We have used the residue imprint information to prevent the non-uniqueness issues. And also, sensitivity analysis have been carried out. We want to know which parameter affect the stress strain curve dominantly. Here comes my last study, that is to upscale micromechanics to macromechanics, because we already get the microstructure information, and also we have got the micromechanics properties of each individual phase. Therefore, we want to know the micromechanical properties of granite. So here we use two different methods. One is the monotonic method, and another method is called the AEH method. According to the AEH method, we can obtain the grain scale stream as well as the grain scale stream during when our sample subject to the high temperature as well as the high load. So that's all of my research, and here is my WeChat. Please feel free to contact me if you have any questions. Thank you.